Hi, we are going to take the same problem and work with this problem to demonstrate the sensitivity analysis and integer programming capabilities of the LINDO. Again, the same problem is taken, and as you see, I have created the solution and the final tableau of the problem. As we look at the problem, the solutions are given in here. Now this time, instead of just solving it regularly and every time that we went to the range analysis and we said no, this time we are going to say yes, and we will see what the results will be. The results that are given to us in here, again the same solution for the problem. It gives the same solution that we had for the optimal solution and for the values of the basic variables and the slacks. However, it adds a new section with the name of ranges in which the basis is unchanged. You would look at two sections. One is the objective coefficient ranges, and as you see, the numbers 4, 3, and 5 are the same numbers that are used in the actual problem. These are the coefficient of the objective function, the vector c, as we know that. The second part of the range analysis, which is provided, the sensitivity analysis, is on the right hand side values. Notice that these are the same right hand side values that are provided in the problem. These values, the result of the sensitivity analysis, can be thought of the ranges in which, if these changes occur, there is not going to be a change in the final basis, the optimal basis. Look at this example for the C1, which is the coefficient of x1. The current value is 4. The allowable increase is 2 units, which is basically saying that as you are going up 2 units from 4 to 6, and allowable decrease, which is 1 unit, which means if you're going from 4 to 3, in this range between 3 and 6, as long as the changes are in that range for C1, then the optimal basis will not be changed. The same is true for examples on the right hand side. For example, if we take B2, which currently is 20, the allowable increase is 39.99999, which is really 40, and the allowable decrease is 5 units, which makes it 15. Therefore, when B2 can change between 15 and 60, if the changes are on that range, then there is no change in the optimal basis. Same is true for B3, but in this case, allowable decrease is infinity, which basically means that B3 can be changed to minus infinity, so there is no restriction on that. The way that it is written is just as long as B3 is less than or equal 56. This type of sensitivity analysis is going to give us a lot of information and a deeper understanding of how the problem is reacting. Let's just save the work, we're going to save the work the same way that we talked about it in the previous video, in the first section of the LINDO. We are now going to be looking at the same problem again, and in this time we're going to look at solving the problem as integer programming problem. Look at the current solution. They are non-integer 3.333 and 13.333. X3 of course is 0, which is integer, but let's see how we can solve a problem like this. The only thing that you need to really do is at the end, after the end statement for the problem, you need to type general integer, and put a number. For example, in this case we have 3 variables. If it is a pure integer program, then the solution is going to be integer for all of them. As you notice, 4, 12, and 0 are all integer values. The new optimal solution is 52. If we don't want to have all variables as integers, so if we want to treat it as a mixed integer programming problem, the only thing that we need to do is just add the variables that need to be integer. In this case, I have put gen x1, which have created the integer value for x1. Notice that x2 and x3 are non-integer because it wasn't part of the requirement. Now let's say that we want x1 and x3 to be integer. We just add another gen statement to the problem. As you're looking at, the x1 is now 3, x3 is 0, and x2 is the other value in here, which is 13.5. As you notice, it is not integer because that wasn't part of the requirement of the problem.